Hello, everyone. As mentioned, I'm Matthew Milano, and I'm here to talk about a language for mixing consistency in geodistributed transactions. We have quite a lofty goal. We want to use information flow to enable transactions which operate over multiple consistency models. What could that possibly mean? Let's start with transactions. As we've literally just heard, transactions are an excellent abstraction for concurrent programming. The core idea behind transactions is that it allows programmers to group operations in a sequence so that the entire sequence appears to occur atomically, as though they were holding one big global lock. Of particular interest to us is the atomicity properties of transactions, which says that all of our mutations appear to occur instantaneously. Transactions are an incredibly powerful mechanism, but in a geodistributed setting, they turn out to be somewhat hard to rely on with the strongest semantics you could want. To see why that might be, let's look through an example. Let's say that I want to implement a mailing list. I've got some users, and I've got this maintenance log on the bottom of the slide. And I'm going to make my users join some number of different groups. And the idea is that users of a group, say the red group, can send messages to other people in their group. And for maintenance purposes, we'll log those messages. So using our very strong consistent transactions, let's implement mail delivery for this example. You could imagine this simple while loop. Here, assuming we have an iterator that goes through the members of our group, all that we do is for every inbox, we insert a post, so every user gets our post, and then we log the fact that we've done that. Exactly what we needed to do. And we're going to use a linearizable database with strong transactions for this. Linearizability is a really strong and simple to reason about consistency model. Now we go to run this, and we're going to discover that it's actually too slow. So why is it too slow? This has to do with our setting. We are geodistributed. What this means is that rather than have our database located in a single physical location, our database is spread across the entire world. Individual variables, say x here, can exist on multiple continents simultaneously as replicas. When we try to update our variables, we need to update them in all of these different continents simultaneously. And a big difficulty for us doing that is that the speed of light is surprisingly slow, at least on this big a scale. If I want to hold a single, literally global lock, I'm going to have some trouble. This makes strong, truly as strong as you could want transactions, a little bit too expensive. Now, we're not out of luck here. In fact, industry has seen this and dealt with it by trying to turn to notions of weaker consistency. Now, there are a lot of different weak consistency models, but what they share is that individual updates to these replicas don't necessarily always get propagated instantly. So we could update x in one location, independently update it in another location, without synchronizing between the two. And it's up to the underlying system to reconcile the fact that we've done that. So let's try to use a weak consistency model to speed up our mailing list. In particular, we're going to choose causal consistency. Now, we've heard a little bit about causal consistency earlier today, but just to go over it again, the properties we're looking for out of it here is that, say, replies will come after the messages they're replying to, and that our session order is respected. That seems like important conditions, and maybe they'll be enough. So we run this with causal consistency, and we're going to have a problem. In particular, we're going to send our message to too many users. The reason we're able to do this is because our view of the group was stale. Some other person on some other continent updated the group, and their update was eventually serialized before our delivery. So that's a problem for us. OK, so we can't quite use causal consistency. But now we have a little bit of a problem. We've tried causal consistency, and let's say we've tried a lot of other weak consistency models, and we find that all of them are not safe for our particular transaction. But we really like that they're low latency. Meanwhile, when we tried strong consistency, our latency was just too high. So maybe what we should do is use both. All right, so let's try to use both. In fact, we're going to use 3 different consistency models. We liked the property where messages are ordered by causal consistency, so we'll put individual inboxes on a causally consistent data store. Our groups were really not working with causal consistency, so we'll make those linearizable again, strong model that we wanted in the first place. And that log that I keep forgetting to mention, let's make it eventually consistent, a very weak model that says that we don't lose updates, but it doesn't guarantee what order they'll be seen in. All right, let's say we want to do this. Instantly, we have a problem. There is no available transaction mechanism that can talk about using different consistency models in one transaction. So what we could try to do instead is maybe run 3 different interactive transactions simultaneously. That doesn't sound like a great idea, and it turns out it's not. One of the errors you might not have seen coming, among the many you may have seen coming, is that if we use our multiple transactions, we're going to potentially abort one of them, at which point we're going to need to replay. But if we don't remember to abort all the other ones, we're going to have multiple messages being delivered. And actually, it gets a little bit worse than that. Some consistency models, especially weak consistency models, don't even have a notion of abort. You can't choose to roll something back. So this isn't going to really work out for us. We're stuck. We can either write a tortured implementation using a weak consistency model and trying to make sure that we're okay despite its idiosyncrasies, or we can give up. But either way, our simple while loop is not going to be what we're using. And this isn't just a problem for this hypothetical example. Consistency errors abound. They've been a wonderful source of research papers for us and of terrible headlines for our companies. What we need, and what these companies' programmers need, is actual guarantees. We don't want surprises that weak consistency can give us. We want the ability to say that certain data is important and it should have strong semantics. We want to keep atomicity. If we're going to try to mix consistency like I'm suggesting, you want to actually have a notion of transactions that you can still use. We want to do all of this without any unnecessary slowdowns. We don't want to go back to the old linearizable world. And as an added bonus, I'm going to try to do this while maintaining legacy system support, which means you can still use data in old transaction systems that don't support a notion of mixing consistency. Now, this might seem a little out of reach or a little hard to handle, and it is. But I think one of our primary difficulties here is the way we talk about consistency and the way we tend to formalize it. Consistency talks about sequences of events or observations or sequences of actions and operations. But our programs, our database programs, are derived from observations on data and actually are just functions of data, which means that the question we're asking is really not what sequence of operations is permitted, but how consistent is this individual variable going to be when I get to read it. So rather than just being viewed as a property of operations, I think that we should export consistency as a property of data. And we think that. So we're going to run with this, and we're going to use it in our language. Our language is going to treat each individual variable as though it has a single consistency model. It's going to have that associated with it. Transactions will still be able to access multiple variables, each of which may have its own consistency model, and therefore transactions need to be able to run against multiple consistency models simultaneously. In order to avoid those surprises we don't want to have, we're going to use an information flow type system with this association. And again, I'm promising legacy system support. So you totally believe me now, everything's been explained, we're all good. Let's just see how that example works. So I have our mailing list. We've already managed to associate our various objects with a consistency model. And our while loop now, if we color our consistency models, looks like this. Our iterator is strongly consistent. Our inbox is going to be causally consistent. And our log will be eventually consistent. Now, this isn't the whole story, obviously. Just putting a bunch of consistency levels in a transaction doesn't necessarily mean everything's going to work out fine. Let's extend this mail delivery transaction to see why. In particular, I'm going to introduce a contest. I want to encourage more people to join my mailing list program. So I'm going to say that we're going to divide our users into 2 different groups, Group A and Group B. And whichever group manages to deliver the most messages to their group mates first is declared the winner of my contest. We're going to say the contest is over when they've delivered 10,000 messages. So I'll enhance my transaction with this code. This code might look a little complicated. All it says is if team A hits 10,000 before team B, or vice versa, we declare the person who hits 10,000 messages the winner. Now, we just got bit by weak consistency, so we're going to be careful this time. And we're going to make sure that declare winner operation here only manipulates data with linearizable consistency and lives entirely in a linearizable regime. But this isn't going to be good enough for us. Our inboxes are what ultimately determines our winner here. Both teams can be declared winner if an inbox is updated in, say, Africa for team A and an inbox is updated in Siberia for team B. Both of those individual replicas can see the 10,000th message and think that they've done it in isolation. The fact that we were linearizable didn't buy us anything on declare winner. As may be suggested, our problem here is this flow. Our problem is that we were able to decide to do a strong action based only on an inconsistent observation. This is an invalid influence, and we're going to want to ban invalid influences. We say that an invalid influence happens anytime a mutation at some level depends on an observation at a weaker level than that mutation. We're going to be able to order our consistency models based on which ones are stronger or weaker by looking at what sort of behaviors they allow or what sort of properties they can enforce. In general, we can actually build a lattice of consistency models. This might seem a little daunting, but it's actually been done. A couple of years ago at this conference, a paper with the consistency lattice was presented. So we have our consistency lattice, and we've associated data with individual consistency levels. Using these two pieces of information, we can implement an information flow type system. And we have. Information flow type systems capture exactly that kind of surprise we wanted to avoid. They prevent both direct bad flows, like when I read a weak variable and just directly assign it into a strong one, and indirect or implicit flows, like that if statement that we saw earlier. And information flow type systems are incredibly well studied in the security literature. So MixT's information flow type system is actually quite standard. This slide has way too many consistency rules on it. You do not need to read these typing rules. But the point of this slide is that these typing rules are not too different from what you would have seen in an integrity information flow system. With only the slightest of tweaks, we could just immediately use it in the consistency space. With this type system, you'll find that the mail delivery transaction we started with is actually perfectly correct. Our inbox inserts a post, and that operation depends only on an iterator, which is more consistent than our inbox. Our log, which is our least consistent thing, has nothing that depends on it, so we're able to use it without worry. This is information flow safe. Meanwhile, the extension we tried to make has those bad flows I was talking about. This dependence between the inbox and the declaring of winner is caught by the type system. Now you might say, but I want to do this. I want to have this contest. To do that, you'd need something that is referred to as endorsement in these type systems, which allows you to have local violations of the guarantees the type systems provide. MixT has a facility for endorsement, but it's a little bit not going to fit in this talk, so happy to talk about that offline or take questions. So we have a type system, and it can prevent some classes of surprises we want to prevent. But I promised, and I keep promising, this notion of legacy system support. So we're going to need to be able to compile down to a sequence of single consistency transactions. Looking again at our mail delivery, we have an information flow guarantee. That guarantee says that everything that is of a strong consistency level does not depend on things of weaker levels. It's the core idea. And what this means is that you can actually operate all of the strongly consistent things before you need to operate less consistent operations. We'll be able to take this and compile it into a sequence of traditional transactions with one transaction per consistency model in play. First running the linearizable operations, then running the causally consistent operations, finishing eventually with the eventual operations. The output of our compiler looks something like this. We take our compiler and we first generate a phase that goes through the iterator, our strongest consistency model. We see that we need to use our iterator in subsequent phases, so we'll record the values that it takes on during this loop. In the next phase, we're going to use that recorded iterator and go through it again, reusing the values we've stored to learn what inboxes we need to insert posts into. Because we're going to need the result of that insert for our maintenance log, we'll also record that. Finally, our eventual phase can just take care of the maintenance log. This all makes sense, I hope, but there's something that's missing here. In particular, what about atomicity? That was kind of the whole point of a transaction. To remind you, our desired atomicity guarantee is that all mutations appear to occur simultaneously. Or put equivalently, that no transaction can possibly read uncommitted or partially committed state. And our problem is that there's no way we can assume multiple transactions on legacy stores have a mechanism for handling this automatically. In particular, we're going to take our transaction, we're going to split it up, and we're going to fear that some interloper can insert himself in between our transaction phases. This interloping transaction may be able to read what's going on in phase 1. Now, there's actually something a bit surprising here about the way MixT's phases tend to work. As is potentially clear, this is only really a problem if phase 1 performs writes. Otherwise, our interloper has nothing to read. The transactions that we've implemented under MixT, and the transactions that we expect to be the most common, have a tendency to cluster their writes in a single phase. So if that's the case for this transaction, which it would be if this were mail delivery, then our interloper would either read all of the writes the transaction will perform, or will simply have nothing to read, so there's no problem. Now, of course, this isn't true in general, so there may be multiple writes for our interloper to view. If there are, we use something called witnesses. Now, in MixT, witnesses are just our specific kind of implementation of locks. But the way we implement them doesn't require any external locking service or custom commands or operations. We implement them directly using the underlying transaction mechanism, piggybacking on the transactions the compiler is already emitting for these phases. The compiler takes care of putting the lock commands in. It's not something the user has to think about at all. Let's talk about implementation. And that's coming next. Let's talk about implementation. So we actually implemented this as a deep embedding in C++, which means that our compiler is a completely separate component that nonetheless runs during compile time of C++. This is an unusual technique, and it does have significant benefits. If, for example, you want to use this in your existing program, you don't have to worry about whether or not we support the version of C++ you're using. You can just include our libraries and move on with your transactions. It did, however, take a little bit of effort to write this code. And if you're interested in seeing more, the code is available. We have it on GitHub, a nice little website. Now, of course, the goal behind all of this was to write our transactions without falling prey to them being too slow. So there are some important performance considerations to take in mind. What we found is that on the most common transactions our examples will have, the MixT version runs significantly faster than the purely strongly consistent version, which we found was too slow. So putting that all together, we're going to associate consistency models directly with data. And we're going to be able to use information flow types based on that association to prevent the kind of surprises that we don't want to have in our programs. That information flow analysis means that we can actually compile our transactions into a sequence of single consistency transactions suitable for operation on any number of legacy databases. Finally, to introduce atomicity to that compilation, we have a mechanism called witnesses. So that's all I have for you today, and I'm happy to take your questions.
Hi.
Hi.
So I'm interested in the connection between, or possible connection between this and the C++ memory model, which, I mean, there's obviously a strong correspondence between the consistency models you get for distributed systems and the consistency models you get for memory in multiprocessors. So in particular, the C++ memory model, you've got several consistency models all sort of playing together in the same language, like acquire, release, and sequential consistency and relax and so on. I mean, have you? I just wanted really if you had anything to say about that connection, and also in the C++. I guess one difference there is that the consistency is per operation in C++. You know, it's an acquire load rather than acquire for that data, whereas you're doing it for the data.
So I think that the domain in which we are most applicable is absolutely distributed memory and distributed systems as opposed to local shared memory. One of an incredibly common pattern in local shared memory is to, say, observe something with a weakly consistent operation, then see that it provisionally has the value you want, go back and observe it with a strongly consistent operation to make sure it really did, and then do something with it, which is not at all what our system expects you to do. Our system is here so that you can bridge these different consistency models where there is no formal understanding of how they work together, whereas the C++ memory model devotes perhaps the majority of its pages to talking about how these observations work together. Certainly, you could use this for shared memory. There's nothing about it that requires you to have a database. You could just use it for memory. I'm not sure that it would give you exactly the benefits that we were pitching.
Thank you.
You said that every transaction for a given consistency level was run in a single transaction. Does that mean that all the data for a given consistency level needs to be stored in one unified database?
So effectively, yes. We need whatever the storage mechanism that holds a given consistency level's data to be able to coordinate transactions. So it can be in an incredibly complex distributed database, or it can be in an open-ended database that knows how to coordinate transactions with its peers. But ultimately, the system needs to be aware of where all the linearizable data is, say.
So you use the information flow type systems?
Yes.
In which case, of course, the low type can, low principal cannot read high data, right?
That was the goal, yeah.
But you can actually write into it.
So we do have to. Sorry,
yeah. So the question is, do you actually need this type of expressiveness for information flow type system, or you just need some strong separation among these three different category of data?
So you could certainly run with strong separation, but you really do want to allow somewhat more expressiveness, because even in the examples I showed, we're talking about deriving rights to lower labels in the lattice from higher labels in the lattice. We also like the idea of allowing you to do blind writes, say, which is something you need more separation for.
So your example requires to use these aspects, otherwise it wouldn't type check.
Yeah, our example would not type check if you just had strong separation between the levels.
Hi, Matt. Excellent talk. Could I ask you to speculate briefly about the possibility of inferring what is the best consistency level for various pieces of data from some higher level specification of what a view of the system ought to be like?
There's actually been work done on that, not by me. I want to call out a paper from 2016 whose authors I just completely forgot. The system name was Quelia. And I think it's quite plausible. If you have a language of invariance that you can associate with your data, then those invariants can be mined to determine whether particular reorderings of reads and writes are going to actually violate them. So yes, I think that's quite profitable.
Okay, thank you.
Okay, well, let's thank the speaker once more.